everywhere on our input space. So that shows the connections with Gaussian processes and the basis function expansion models that we were looking at before. So we said that every basis function expansion model is a Gaussian process. And we said reversely, we can consider any, so this was just an example with the squared exponential kernel. But in general, for every positive definite covariance matrix, there exists a possibly infinite basis function expansion. The covariance function? Or? Did I say, I meant to say the covariance function. I don't know if I said kernel function back there, but if I did, I meant to say covariance function. Yes, so this theorem here is known as Mercer's theorem. So you can see the more detail in Carl's book. Here's the reference there. So for the squared exponential, we have a nice representation. In general, we might not have such a nice representation. Okay, so next I have some examples of different types of covariance functions that we can use and what it implies about the samples from the Gaussian process. So do we have time to go through this? Should we? 20 minutes? Okay. All right, so the first example, the one that we saw on the previous slides, is the squared exponential covariance function. So this is a stationary function, so it's just a function of the difference between x and x prime. And this function is infinitely differentiable, so that means that our realizations, our samples from the Gaussian process, will be smooth. It has two parameters. The first is one is the length scale, L, and the second is the parameter V0. So the length scale, here's some samples for different values of the parameters. The length scale roughly controls the period in which we see a big difference in our function samples. So here's an example with a length scale of 1. We see that as we move 1 point, we can see differences in our sample functions. This is done with all with a mean of 0. So we see that on average, if we average out our samples, we have a mean of 0. And this parameter V0 controls the point-wise variability at each point x. So with V0 equal to 1, all of our samples roughly lie between -2 and 2. If we decrease V0 to 1/4, all of our samples lie between -1 and 1. And if we increase our length scale, you can see that it takes much longer time for the function to change. Okay, the next example is the rational quadratic covariance function. So this function is defined here in this form. You see that this is also a stationary covariance function, so it only depends on the distance or the difference between x and x prime. And it has two parameters, alpha and the length scale L, which are both positive. And we can view the rational quadratic covariance function as a mixture of squared exponential covariance functions with different lengths. So roughly, if we take the squared exponential covariance function here, and we put a prior on the length scale, so here I just set tau equal to the inverse of the squared length scale. So if we put a gamma prior on tau, parameterized as is written here, then I see that the squared exponential is just proportional to this term here, ignoring the V0 term. And the gamma density is proportional to this term here, ignoring the normalization constant. In this case, it's alpha over beta to the power of alpha divided by gamma of alpha. So if we integrate out tau, we see that, well, these two terms can combine to just give us an updated parameter here for the gamma distribution. So we have alpha over beta plus negative 1/2 d squared. And then we can integrate that with respect to tau, and since it's still a gamma, we just have this normalization constant. So we take the updated parameter here to the power of negative alpha. Does everybody see that? So that's just saying that this is proportional to integral of exp tau times negative 1 d squared plus alpha over beta tau to the alpha minus 1 d tau. And here we just have this is just gamma. We just have to add in so in general for gamma we have beta to the alpha over gamma of alpha. So this is the term that we have to add here, which is just 1/2 d squared alpha over beta to the power of negative alpha, since we're missing that term when we try to integrate it to 1. And then you can do a little bit of work and you'll get this form here. Here we just set beta equal to L to the negative 2 to interpret this L now as the length scale. So here are samples of from a Gaussian process with a rational quadratic covariance function. So here are some samples with different values of alpha. As alpha goes to infinity, the rational quadratic covariance function converges to the squared exponential covariance function. So here we see that this green line are roughly samples as the rational quadratic covariance function from the squared exponential covariance function. And here is the covariance as a function of the input distance. So here we see that the covariance function drops off much faster for the squared exponential. And this alpha roughly controls how much we remember as a function of the distance. Okay, let's look at one more class of functions, the Materne covariance function. So in general, this has this form here, which may look quite complicated. It has two parameters, V and L. So L, again, is like the length scale that we saw in the previous examples. This is another example of a stationary covariance matrix, since it only depends on the difference between x and x prime. And if V is equal to a natural number plus 1/2, this actually simplifies a bit. And sample functions are, this is just denoting the smallest integer less than V. So for example, if V is equal to 3.5, sample functions are 3 times differentiable. So this parameter V controls how smooth our realizations are. So let's see some important examples of this type of covariance function. So if V is equal to 1/2, this is the case where we have something which is nowhere differentiable, right? Then we have the Laplacian covariance function. We just have Brownian motion. So that corresponds to this, the covariance function in that case simplifies here. If V is equal to 3/2, our samples are once differentiable, and our covariance function simplifies to this form here. 5/2, we have it's twice differentiable. And as V goes to infinity, we have the squared exponential function. So we have something which we said is infinitely differentiable. So these are probably the two most often used in the two examples. Well, not considering this really as an example of, since it's a limiting case of the Matern covariance function, these are the two which are most widely used in machine learning. Mm-hmm.
I do not know what kind of functions and how to choose them.
Yeah, so you see that a lot of these covariance functions have different properties. So if you want your function to be smooth, to be stationary, I mean, this is a general problem. How do you choose the covariance function? If you want it to be smooth, you can, for example, go to the squared exponential function. You'll see these ones give much rougher realizations. We'll see. Ah, okay. Oh, yeah, so basically if there's some properties that you want the covariance function to satisfy, that could do some computation of what types of covariance functions to choose. But that is a big modeling choice when using
I can also add that the last week, we saw that in the Bayesian approach to machine learning, we could compare the performance of different models using this distribution, which is basically the probability that each model gives the data. If we have, if we have different Gaussian processes with different covariance functions, each of these Gaussian processes represents a different model for the data. So we could evaluate this normalization constant in the joint distribution, and we could use that to select one Gaussian process or the other. The problem is that sometimes evaluating that normalization constant is expensive, and taking into account the properties of the covariance functions can also be useful. If you know that your data, for example, is going to be very smooth, you should use this squared exponential covariance function, because you can compute all the derivatives, and if you don't expect your latent functions to be smooth, you can choose other covariance functions.
Yeah, so just to continue on what Miguel said, you can look at the choice of the covariance function as modeling choice and use model selection tools to choose what type of covariance function you want. And there's actually some work also in our group in actually putting a prior on the covariance function. Yeah, but I won't discuss that. But if you're interested, we can provide you with some references for that case.
Can you show us these three interfaces V, and they're always multiples of 1/2. I'm wondering why these are spectacular and
that's because this simplifies. If you look at this, so this kv is the modified Bessel. This function simplifies a bit if I set it equal to a natural number plus 1/2. So that's why that's to simplify things a bit here. Okay. So here's some realizations. So this is for v equal to 1/2, the blue one. So this we see it's Brownian motion. We have very rough sample paths, something which is not differentiable. For v equal to 1, slightly smoother. This is 1 times differentiable. The black line, we have something which is twice differentiable, and then we have the green line, which corresponds to the squared exponential function. So we get something which is infinitely differentiable. I should also say that when using the covariance function, sometimes people have information on the derivatives of the covariance function. So in that case, so sometimes the squared exponential might be easy to work with if you have, you obviously want something with a derivative if you have some information on the derivative.
So if you work with time-initial data, you use non-derivative parameters, or?
You use the Brownian motion?
Yeah.
Yeah. Yeah. Yeah, so you saw the connections between the finite regression model, the basis function expansion models, and the covariance and the Gaussian processes. So you can see a similar choice. For those, we have to choose the basis functions. Here we have to choose the covariance function. And you see that obviously our choices have a big difference in what our what possible samples look like from our model. Okay, then we just have periodic covariance functions. So one way to define a periodic covariance function is just to map our input space x to a vector u, which is a two-dimensional vector containing the sine of x and the cosine of x. And then we can just combine it with one of the, measuring the distance in this space u, and combine it with the squared exponential covariance function. Or any covariance function, for example, the squared exponential function. This will give us smooth periodic functions, obviously, if we combine it with the squared exponential covariance function. So if you work out what the transformation in this case is, you'll get you'll get this form for the covariance function under this transformation here. I should just say that if you actually work this out, you'll get 1/2 here. So here I've just rescaled the data by times pi, so that we have a period of 1. So here you can just think of this as the period divided by 2. So here's some samples using this transformation combined with the squared exponential function. So you see here we have a period roughly of 1. We have a large length scale on the left. So we have quite smooth, non-varying samples from our prior here. Instead, with L less than 1, a small length scale, we get something that, well, it's still smooth, but it's much more wiggly. Again, this is the same period, a period of 1 here. Yes, you can. Yep. Yeah. So far I haven't talked about how we actually learn these. I mean, the choice of these these parameters, the length scale, the V0 obviously has a big effect on our samples. So these parameters are usually learned from your data. So one way would be to put a prior on these parameters. Okay, and multivariate extensions. Multivariate extensions can be obtained, for example, by so in all the examples that I just showed you, I assumed that x was just a real number here. So we can create a multivariate extension by just replacing this squared term by some general distance in a multivariate setting. So for example, if it's diagonal, if the matrix M is diagonal, we just have the sum of squares. So in the squared exponential case, this could correspond to using a different length scale along each dimension. So here's some examples of samples from a Gaussian process with two-dimensional input. And we have different length scales along each dimension here. So you can see we can have something which is more wiggly in one dimension and varies less frequently in the other dimension. Okay, and then I guess I have time to just finish off real quick. Okay. So inference. We said that these parameters for the covariance function have a huge effect on what type of functions that we see. So often these parameters, they are learned from the data. So if we let theta to denote all of our parameters, so the parameters of the covariance function, and say also our noise variance, sigma squared, then, well, the covariance function is often, that is something that you have to choose. But we can learn about the parameters of the covariance function. And one way to do this, one way that is often done, is just to find the parameters which maximize the marginal likelihood. So that's the likelihood of y with the function f integrated out. And so we said this has a nice form. It's just normal. So we just find the parameters which optimize this marginal likelihood there. And that's what is typically done, but obviously another way to do it is to put a prior on the parameters. That's more of a Bayesian treatment, but in practice this is what is usually done. Okay, and so that's it. Again, here's the references. So if you want more information on Gaussian processes, I encourage you to look at this book. It's very easy to read, something that you can read while going to bed. So.
Thank you, Sarah. Thank you for your lecture. Do you have any more questions? We still have about 5 minutes. Are there any more questions? No? Okay, so thank you. And hopefully I will see you tomorrow again.
Can you